You know, AI, it can feel like a total black box, right? We see all this incredible stuff it creates, the art, the conversations, the recommendations, but what's actually going on under the hood? It feels like magic, but I'm here to tell you, it's not. It's math. And today, we're going to open that box.
So let's do it. Let's crack open that box and see how this thing really thinks. Because behind every single smart reply or personalized playlist, there's a structure, and it's surprisingly elegant, and you know what? It's totally understandable. Let's take a look.
That's the secret. The entire mind-bending world of modern machine learning, it's basically built on top of just 4 fundamental pillars of math. If you can get your head around these 4 concepts, you'll understand the core logic of pretty much any AI system out there.
So our first pillar is linear algebra. And hey, forget any nightmares you might have from high school math class. In the world of AI, this isn't about abstract problems. It's the language we use to speak to data. It's like the grammar that turns all the messy chaos of the real world into something a machine can actually work with.
Think about it. Before an AI can learn a single thing, it needs data in a language it can speak. And that's exactly what linear algebra does. It gives us the rules to translate everything, from your movie ratings to a medical scan, into these nice, neat, organized grids of numbers.
So how's that work in practice? Well, imagine a single person's profile on a website. You've got their age, their location, maybe their income. To a machine, that's just a list of numbers. In linear algebra, we call that list a vector. It's basically just one row in a giant spreadsheet.
Okay, so now picture stacking all of those individual profiles, all those vectors, one on top of the other, thousands, maybe millions of them. What you get is a matrix, and this giant grid is the exact format that pretty much all machine learning algorithms are designed to understand.
But what's the big deal about organizing data this way? Well, here's where it gets really cool. Imagine your data has, say, 1,000 different features for every person. Finding a pattern in that is nearly impossible. But linear algebra lets us do something amazing. We can project all that messy, high-dimensional data into a much simpler form. It's kind of like taking a complex 3D object and just looking at its 2D shadow. This whole process is called dimensionality reduction, and it helps the AI cut through the noise and focus on the patterns that actually matter.
All right, so linear algebra gives our data a nice, clean structure. But how does the AI learn from it? I mean, how does it actually get smarter? Well, that brings us to our second pillar, calculus. If linear algebra is the grammar, then calculus is the engine that actually powers the learning process. I mean, a model is never perfect right out of the box. It makes a guess, it's wrong, and then it has to get better. The big question is, how does it know what to change to improve? How does it know which direction to go in?
It all starts by measuring just how wrong it is. In machine learning, this measurement of error is called a loss function. You can think of it like a score in a video game. A really high score means you're way off, and your goal is to get that score as close to 0 as you possibly can.
And this is where calculus has its superhero moment. It gives us this incredible tool called the gradient. The gradient is like a magic compass that always points in one direction, the direction of the steepest, fastest increase in error. Basically, it points straight uphill into the land of wrong answers.
And once you know which way is uphill, the learning process becomes, believe it or not, incredibly simple. It's an algorithm called gradient descent. Step 1, you use calculus to find the gradient. Which way is up? Step 2, you take one small step in the exact opposite direction, downhill. And step 3, you just repeat that again and again, taking little steps downhill until you finally reach the very bottom of what we call the valley of error. And that, right there, is learning in a nutshell.
Okay, but we all know the real world isn't some perfect, predictable valley, right? It's messy. It's uncertain. An AI model can't be 100% certain all the time. And this brings us to our third pillar, probability and statistics. This is what gives AI the logic to handle all that real-world messiness. So a less sophisticated model might just give you one rigid single answer, like the price of this house is exactly this number. But a much smarter, probabilistic model can express its own confidence. It doesn't just give you a number, it gives you a range of likely outcomes and a probability. And that is so much more useful for making actual decisions.
And visually, that kind of answer looks a lot like this familiar bell curve. It's not just one guess. It represents a whole distribution of possible answers, showing that some are way more likely than others. It's the model's way of saying, look, I'm pretty sure the answer is somewhere around here.
At the end of the day, that's what probability theory is all about. It gives these models a language to talk about nuance.
It's the huge difference between a machine that says, I know, and one that can say, I think, and here's how sure I am.
And this brings us to our fourth and final pillar, the one that really ties everything else together, optimization. You can think of this as the master strategy for the whole operation, the quest to find the absolute best version of our model.
Remember that whole downhill journey we were talking about with calculus? Well, optimization is the formal name for that entire process. It's the overarching mission to constantly tweak and adjust the model's internal settings, always guided by the gradient to find that one perfect combination that gets our error, our loss function, as low as it can possibly go.
Okay, deep breath. Let's put all 4 of these pillars together now. Let's imagine we're building a really simple AI. Its only job is to predict someone's salary based on their age. So, how do all 4 of our pillars work together to make that happen?
Well, first up, linear algebra swoops in and organizes all our messy age and salary data into clean, usable matrices. Next, calculus gives us the engine, gradient descent, which starts adjusting a predictive line to make fewer and fewer mistakes. Then, probability lets our final model be more useful by giving us a confident range for its salary prediction, not just some random number. And finally, optimization is the name for the whole goal, the mission to find that one single line that best fits all the data. See? They all have a job to do.
And that's really the big idea here. Machine learning isn't some unknowable magic. It's an elegant system built from the ground up with these fundamental and frankly beautiful mathematical tools. Each one has a clear purpose, and they all work together to create the intelligence that we interact with every day. So the next time you get a movie recommendation or you ask a chatbot a question, try to peek inside that black box. What will you see? Will you see the organized data structures of linear algebra? The step-by-step learning of calculus? The careful confidence of probability? Because once you know about these pillars, you really do start to see them everywhere.